We tried to make this a peak until Friday late afternoon. So if anybody wants to talk to him, then there's plenty of opportunity.
Okay.
Okay.
Well, first of all, I'd like to say thank you for having me. I've been made to feel very welcome since I've been given a desk and everything. So, thanks for that. So I'll be talking about my PhD in quite general terms today. I'll include a couple of examples I've been working on. But mostly my PhD has had to do with kind of the intersection between intrinsic noise that occurs in individual-based models and non-Markovian effects, which can also sometimes occur in these kind of models. Now I'll kind of define the terms as I go along for you. To give you just a brief overview of what we're speaking about, first I'll kind of talk to you about exactly what I mean by intrinsic noise and individual-based models and how this intrinsic noise can come about in these models. I'll then go on to tell you how you can quantify this kind of noise in the simple case when you have no memory in the system, so it's Markovian, and also in the more complicated case where you don't have memory. And then I'll go on to give you a couple of examples. So this is the very developmental biology focus. So the first one is in the somite segmentation clock, where you have noisy cycles of gene expression. And the second example will be in Turing pattern formation, which is kind of spatial patterns which get produced in reaction-diffusion systems. And I'll kind of allude to how you can get individual-based noise and non-Markovian effects in these kind of systems. Okay, so to start with, then let's talk about what exactly I mean by an individual-based system, because I'm sure a lot of you will have different ideas of what this might mean. So basically, imagine a box of particles, and these particles, they interact in a stochastic manner, and they all have different types of flavour, let's say. And the result of an interaction, for example, might be an A-type particle meeting a B-type particle, and the A-type particle, as a result, being converted into a B. And I emphasise that this is a random process. So with a certain probability per unit time, these kind of group interactions will occur. And these A's and B's, these might represent, say, predators or prey in an ecological model, or perhaps different opinions in an opinions dynamics kind of sociological model, or perhaps different chemical species, things like this. And the intrinsic noise that comes about in these kinds of models is the fluctuations in particle numbers of the A's or the B types due to the fact that we have finite numbers of particles and the fact that they interact in this stochastic manner, as I say. So we can also include spatial effects in our models, so we could have different boxes, if you like, where particles could hop from box to box, or perhaps the rates with which the particles interact over here might be affected by the numbers of particles over here and so forth. So this is quite general, these types of models that we're talking about. And the Markov assumption that's commonly made with these types of models is the idea that at any one time, the reaction rate in the model, or the time evolution of the system, is only governed by the current state of the system. And as I'll show you, this isn't always an assumption that one can make. But if one can make this assumption, then the way that one deals with these kinds of models and the way that one quantifies this intrinsic noise is by writing down the famous master equation. So I'm sure many of you will be familiar with this equation, but I'll explain it even so. What this quantifies essentially is the probability that at any particular time t, given a particular starting condition, that the system ends up in a state denoted by this vector n, which basically is telling you the different numbers of particles in the system at the various different times. And in order to evaluate this equation, you have to be given basically what comes from the model or your system is the reaction rates. So this is the probability per unit time, that given that the system is in a state n, that the system will change its composition by a vector r. So this is fairly straightforward, but one should note that these reaction rates only depend upon the current state of the system. This is where this Markov assumption comes into the model. Okay, so the master equation can only be written down in the case where you can make this Markov assumption, essentially. So this master equation can be solved in certain simple cases, but in general it can't. And one often makes a simplifying assumption that the numbers of particles in the system is large but finite. And if you can make this assumption, then you can use an approximation scheme known as the system size expansion. So basically this follows this kind of reasoning. So we start with our master equation. We define a system size parameter which tells you the typical number of particles in the system of the various types. One which scales the variables in the master equation according to this system size parameter, and then we expand in inverse orders of this parameter which we assume is large, and we truncate the series at the second order, and we obtain a Fokker-Planck equation. Now this Fokker-Planck equation, through Ito calculus and so forth, can be shown to be statistically equivalent to a set of Ito SDEs. So these Ito SDEs, basically this is approximating the full dynamics of the system with a deterministic part and some Gaussian noise. And we're kind of approximating the particle numbers now to be a continuous quantity. So you can read off this deterministic part from the Planck equation, as well as these correlators. Just to emphasise this, so we have this. Yep, sure.
Isn't the noise depend on n as well? The n is not doesn't disappear, right? The system size.
So I've undone the rescaling going from here to here. Is that what you're asking?
Oh, this one was copy variables.
Yes. Yeah. Is that clear?
I'm using the n instead of having the focal plan. I'm using the variables.
So I've skipped a step out essentially. So I've absorbed the. Okay. So n times x is. Okay. So we have this deterministic part and this intrinsic noise part. Now, so if I were to ignore this intrinsic noise term, set this equal to 0, which would be accurate if we had an infinite number of particles, and I would recover the kind of deterministic dynamics that one might naively write down if we were just to write down the mean field equations, let's say. But what's nice about these stochastic differential equations is that you can calculate the moments of the particle numbers. You can calculate probability distributions in some circumstances, but rather crucially, you can calculate power spectral fluctuations, which I'll come back to. This is what I use an awful lot in my work. Okay. And so just to give you a really simple example of this, so a particle process. So we add a particle to the system with a constant rate per unit time, and this is what we get if we simulate this. So roughly the system, we get this kind of straight line, the numbers of particles goes up linearly with time. We can perform our system size expansion type thing, and we end up with a stochastic differential equation which approximates these dynamics, and of course they look qualitatively similar when we run it for long enough. Of course, if I was to zoom in here, then you'd see the discrete nature of the model, and it wouldn't look anything like the SDE down here. So this is only valid when we've got large numbers of particles in the system. And you can also quantify the probability distribution of the number of particles in the system at a particular time, and you can see this is approximated nicely with the Gaussian distribution that we get from the SDE. So this is basically your approximating the Poisson distribution for the Gaussian distribution. Okay, so that's just to show you how this can be useful. Okay, so that's the simple case where we have we can make this Markov assumption, but what if we can't write down the master equation and perform the system size expansion in this way? So some examples of systems which have these non-Markovian effects, which I'll come back to as examples, are gene regulatory systems where we have these time delays due to transcription and translation processes. And also another example is where we have anomalous diffusion, where particles, the rate at which they hop from site to site is dependent on how long they get there. So if we want to quantify the intrinsic noise in these systems, but we can't write down the master equation, a nice way to do this is with a path integral approach, actually. So a path integral, by necessity, takes into account all possible histories of the system. And in so doing, you can write down an expression like this. So we're quantifying the probability at a particular time t that the system is in a particular configuration. And one can write this down as simply the sum of all the probabilities that we go on different paths that allow us to end up in this particular configuration. And so if one can find these probabilities, then one can evaluate this. One can then do the system size expansion within this formalism, arrive at an approximate expression for the path integral, compare this to the path integral for the corresponding SDE, and read off the SDE. So using this path integral formalism, we can arrive at SDEs, stochastic differential equations, in the same way that we did with, in a similar way that we did with Markovian procedure, and we can obtain power spectra, correlation functions, what have you, in a similar way, once we have these SDEs. Okay, so that's roughly all the maths I wanted to talk about, and this is kind of what I'll link together the two examples that I'll show you, so you can kind of have this in the back of your head as I go through these examples, that we can, in these non-Markovian systems, we can still quantify the intrinsic noise. What I'd like to talk to you about now is an example of where these two effects come into play, so intrinsic noise and non-Markovian effects. And so we'll give us an example of the somite segmentation clock. So I want to convince you that in these examples, that it's important to include these intrinsic noise effects, because you can actually get emergent phenomena such as cycles that come about as a result of the intrinsic noise being included that you wouldn't see in a purely deterministic system if you wrote down only new field equations. So the intrinsic noise is important in this sense. And once we do that, I'll show you how this intrinsic noise and these cycles depend on the model parameters that we have. Okay. So, just to give you a bit of background then about the somite segmentation process, it's a really rather nice kind of biological process where in vertebrate embryos, as the abdomen of the embryo extends in utero, you get these blocks of cells which form along what will become the spine, and they form in pairs of blocks, and essentially after further cellular differentiation, these blocks of cells go on to form vertebrae and ribs as the thing develops. And as the abdomen extends here, so this is a zebrafish embryo, you can see as it extends you get more blocks forming, and eventually the thing starts to look more like a spine. And these blocks appear in rather a sequential and systematic manner, which is quite well evolutionarily conserved actually. So lots of vertebrate animals exhibit this process, and it's roughly 20-30 minutes that we get these blocks being formed. And this has been of interest to experimentalists and theorists alike for many decades now, because it's rather a nice example of where microscopic processes on the gene regulatory level can be linked to the macroscopic process of pattern formation or developmental kind of production of the embryo over time. So this is really sort of at the heart of systems biology, this linking of the genetic process to the macroscopic developmental phenomena. So the kind of prevailing theoretical framework for modelling this somite segmentation process, so as you mentioned, so the somites are the blocks of cells. I'm not sure if I said that explicitly, but okay. So the prevailing theoretical framework for this is the so-called clock-wavefront model, which was put forward by Cook and Zeeman in the mid-1970s. So this has really kind of stood the test of time. The idea is as follows. So every cell in the so-called pre-Semitic mesoderm, so this is this sort of region of the embryo here in the tail, which produces the cells which become the somites. Each one of these cells possesses some internal clock, and each of these clocks kind of oscillates in some sort of rhythmic manner, and each of the cells in the pre-Semitic mesoderm agrees on what kind of time it is, if you like. So they all oscillate in unison. And the idea is then that a wavefront propagates through the PSM, and as it does so, when it encounters cells at different points of the cycle, it interacts with them differentially. So if it, and as a result of the interaction with the wavefront, the cells change their adhesive and migratory properties accordingly, and thus the kind of up-down temporal periodicity of the clock in the somites is converted into the spatial periodicity, the temporal periodicity of the cycles in the cells is converted into the spatial periodicity of the somites through the interaction with the wavefront. And this kind of idea has been verified in experiments now. So people think they know what the chemical is that's responsible for the wavefront. So here it says FGF, in some species it's WNT and so forth. And people also think they know which genes are primarily responsible for the clock inside each of the cells as well. So I think what I'd like to do, now is I would like to focus on the clock as opposed to the wavefront, and we'll delve into that a little bit more detail. So, as I've kind of alluded to, the thing that's responsible for the clock or the oscillations inside each of these cells is essentially a gene regulation, or the expression of a particular gene which oscillates in time. And so, basically what that means is that inside every cell you have DNA, which is transcribed into mRNA, which is then translated into protein. And both of these processes are stochastic processes, which occur with certain probabilities per unit time. And these proteins then, they go on to regulate the production of the mRNA. So we've got this kind of feedback loop. And different proteins are interacting with different genes, and this produces what's called a gene regulatory network. And this can give rise to oscillations in the numbers of proteins. Notably, so we've got these stochastic processes, which are, and we have tens or hundreds of mRNAs per cell and thousands of proteins. So the root N effects are really important here. So we do have intrinsic noise in these cells, and the cycles that are produced are noisy as a result. Notably as well, the transcription and the translation processes are delayed. So what that means is they take a certain amount of time to occur, so the amount of mRNA that's produced now and the amount of protein that's produced now is dependent on the numbers of proteins and mRNA in the past, respectively. So we've got this interplay here between this intrinsic noise and these transcriptional and translational delays. So if we want to quantify this intrinsic noise in this kind of model, we're going to have to use this kind of analytical approach. And so what we find is that if we want to kind of build a model of our somite segmentation clock, what we decide to look at is a simple kind of two-cell model where we have only two genes per cell, and the cells are somehow coupled through this delta-notch mechanism. So the idea is that we have our clock gene, which produces mRNA, as I said, which is then translated into protein. These proteins then interact with the other two genes. But we also have these this delta gene, which produces protein, which is then secreted by the cell. And when the protein is secreted, it binds to the notch receptor on the opposing cell, and this then regulates the clock gene in this cell. So this delta gene is responsible for communication between the two cells, essentially. And this is a so-called delta-notch signal. So this is one aspect of our model. We've got these transcriptional and translational delays in here as well, that I mentioned. But rather crucially, the kind of thing that we're in our simulations, we're simulating things on an individual base level. So we're including this intrinsic noise, which, as far as I'm aware, in previous models of the somite segmentation clock, has been kind of ignored. And so what we'd like to do is see how this intrinsic noise affects what we see in our simulations. And this is what we see. So we find that for certain biologically reasonable parameter sets, that we find the deterministic model would express, so these are the kind of mean field equations ignoring all intrinsic noise. If we simulate these, they will exhibit transient oscillations decaying to a fixed point. But if we include the intrinsic noise in our individual-based model, this will have persistent noisy cycles. Now this is really important. So because we want our genetic oscillations to be a viable kind of clock in our clock-wavefront mechanism, we have to have regular persistent cycles in our cells, in our gene expression. So it's quite nice that we get these cycles in the individual-based model where we don't in the deterministic model. So we need to include the intrinsic noise here. And we can quantify this, so we can look at the power spectrum of these cycles in the left-hand panel here. And we see that our theories agree quite nicely with the simulations here. And from this power spectrum, essentially what this is telling you is the contribution of various different oscillatory frequencies to this signal here in the left-hand box.
So do a simulation with I presume, a small system, no?
Quite small. So we've got, like I said in the other slide, so it's roughly tens or hundreds of mRNAs and thousands of proteins. So thousands of particles. So the simulation method, I should say, so this isn't your regular kind of Gillespie simulation. So instead we have to, because it's delayed, we have to use this modified next reaction method, which takes into account the delay.
The thousands is still a big number, no?
Sure, yeah. You can use C++ and it'll do it for you. The simulations take roughly 5-10 minutes.
So for 10,000, intrinsic knowledge is still relevant.
Oh, certainly, yeah. Well, as you can see, right? So we get these persistent cycles here in the individual-based model that we certainly don't in the deterministic model. Okay.
Sorry, going on the previous question, you were saying the number of particles is thousands, but the number of particles, let's say, messenger RNA is much smaller.
Certainly, yeah.
And you say which is the number is 50 or 100 or?
I think so. There's the actual. I think it's about 50. Yeah.
Yeah.
50.
So probably this is really the source of the intrinsic noise property. I mean,
Yes, perhaps.
this is a small number. The particle is in a small number, not the proteins that are in.
But we are looking at the protein. I know what you mean. Yeah. So this is what's giving rise to the intrinsic noise, perhaps. Yes. Certainly the numbers of proteins that we have here, which is like hundreds, isn't it? Yeah. And well, rather nicely, even though we do have these small numbers of mRNAs, the theory which is produced using a large particle number approximation still agrees quite nicely with the simulations. Okay, so as I said, so the peak oscillatory frequency here is telling you about the typical periodicity of the cycles, and the width of this peak is telling you about the coherence of these cycles, so the degree to which these kind of additional frequencies are contributing to the signal. So I'm going to term the width of this peak as being related to the coherence. So this kind of brings up the question, okay, so what kind of properties are we looking for in our cycles for them to be useful as a segmentation clock? And so I've kind of compiled a list of the sort of properties that we need to be viable as a segmentation clock. So the oscillations in different cells, they must have the same dominant frequency, and they must have as little as possible phase lag between the two cells in order for them to agree on sort of what time it is, if you like. So they must be oscillating in unison. Furthermore, so the quality of the cycles in the cells must be sufficiently good for them to be interpreted by the wavefront, if you like. So they mustn't be too obscured by noise, they mustn't be too noisy, so they must be coherent, and they must have a decent amplitude as well. Okay, so what I'd like to know is, to what extent does delta-notch signaling affect the quality of these cycles and synchronization? So it's been shown in experiments that delta-notch signaling does play a role in keeping the cells in sync. So it allows the communication between the two, and it will synchronize cycles. And through biological experiments where they do, they can force mutations in the delta gene. They notice that the cells no longer oscillate in unison. So it's clear that the delta-notch signaling is what's responsible for this synchronization. But what I'd like to know is, how does this interact with the noise in our model? Does it regulate the noise at all? How does this work? So what we do is we have two cells with slightly different internal parameters, ever so slightly different, and such that if we had no delta-notch signaling between the two cells, they would oscillate at different internal frequencies. And then we switch on the delta-notch signaling and we see what happens, basically. And that's what we do here. So without the coupling, you can see that the two cells, they're oscillating with pretty much different frequencies. The peaks and the troughs aren't really lining up at all, and so these are clearly not in sync. And this is evidenced as well by the power spectrum fluctuations, which is different in either cells, different peak frequency. When we switch on the coupling, we we have these much more coherent and synchronized cycles, and this is evidenced by the fact that the two peaks have kind of merged into one peak, and notably the coherence, I think you'll agree, so this is a much more sharp peak. It's greater in amplitude, and now they're agreeing on what the oscillatory frequency ought to be. So we can do better than just looking at these two diagrams, and because we have our theory, we can look at how the various properties of the system vary with the coupling strength of the delta-notch signaling. So if we switch off the coupling, to start with, we have two different peak frequencies of the cells. And as we increase the coupling strength, the frequencies then align rather nicely, and they synchronize. I should say, ignore the green lines for the purposes of this. The blue and the red lines represent the two cells. Similarly, the intercell phase lag between the two cells can be seen to reduce as we increase the coupling strength, so the cells are synchronizing. Furthermore, the amplification, the amplitude of the cycles increases as we increase the coupling strength. And most importantly, the coherence increases. So the cycles in the cells are becoming more well defined in their oscillatory frequencies as a result of increasing the delta-notch signaling strength. So not only is the delta-notch signaling responsible in our model for synchronization of the cycles in the cells, it's also responsible for improving their quality and regulating the noise in the model, making it so that the noise isn't distorting the cycles too much. Okay, so that's more or less everything I wanted to say about somite segmentation clock and noise-induced cycles in such a model. So I'd like to kind of switch gears now to talk about
one question. The results are obtained from the path integral method, so are just another simulation method? Or?
No, so path integral, what we do is so we find the effective process for, so you could write down deterministic equations which looked at the concentrations of the proteins in the mRNAs of the cells, sort of partial differential equations, this kind of thing. What we do is we derive in a rigorous way the noise that's added to these partial differential equations that corresponds to the noise in the individual base model. So we're kind of approximating, so this is what this
But you simulate these stochastic equations?
No. So we calculate the power spectrum analytically. So this black line here is done fully analytical. Well, okay, I mean I have to evaluate the integrals in Mathematica, but I don't have to simulate it. I don't draw any random numbers for the black line, which is what makes it so useful. So it makes it that much quicker, and that means we can write that, we can get these nice smooth lines. So that's kind of the use of the theory in this context.
I guess here there is a dependence on the number of proteins and the number of variables in there. I mean, the infinite number of variables, you have these that the oscillation decay, right?
Yes. 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 So
if the number of particles is very small, or it will be dominated by noise.
Yes, I
So
agree.
it should be an optimal size for synchronization between the two cells.
Yes, I agree. Yeah. So if you're right, and if the number of particles were really small, then we wouldn't really be able to do this kind of analysis for the system size expansion. We'd be out of that kind
So
of.
there's an optimal size for coherent, optimal size for synchronized behavior.
Well, I think you wouldn't be able to define a cycle if there were so few particles that you could really see the discrete nature of the dynamics.
But it depends on the synchronization, right?
Yes, certainly.
And will be optimal for some even intermediate system size.
Yes, I couldn't tell you how I would. Optimum is, well, so if you were in a parameter set for which you did actually have deterministic cycles, and they did, there are parameter sets for which you do get sustained cycles in the deterministic model, and then more particles is better, really. But in this parameter regime where we have these noise-induced cycles, and certainly, the noise-induced cycles would go away as relatively speaking, as you increase the particle numbers. So for the noise-induced cycles, yes, there's this optimum.
Because the tune comes from the amplitude of the right? I think the more particles you have, the more coherent it is. The cycles will be very coherent but tiny. If you have a very large and finite number of particles, they will be coherent but small in amplitude, right? So the optimum comes from probably a detectable amplitude somehow, right?
That's a good point. Okay. So I'll switch gears now. So going away from noise-induced cycles to something that's a bit more spatially oriented. So Turing's mechanism for pattern formation. So here I'll kind of highlight one particular issue with Turing's mechanism for pattern formation and show you that perhaps the inclusion of anomalous diffusive effects and noise in the model might go some way to mitigating the possible issue with Turing's mechanism. So I'll first describe to you exactly what I mean by Turing's mechanism. So in 1952, Alan Turing, working at the University of Manchester, wrote his seminal paper, The Chemical Basis of Morphogenesis. So this has really been kind of subject of discussion for quite a few decades now. And basically Turing's idea was this. So you have two sets of chemicals which would interact with each other in this non-linear manner, and they would also diffuse. And to model such a system, you can write down these kind of nice, simple coupled PDEs with a diffusion term and non-linear reaction terms. And what Turing noticed was that, okay, so ignoring diffusion for a second and just having the reactions, suppose we could have a set of reactions for which the well-mixed system tended towards some sort of stable fixed points. Okay? Now you introduce diffusion. What Turing showed was, so I mean, what maybe naively you would expect if you didn't know about Turing pattern formation would be that, okay, diffusion is kind of a stabilising influence. We have a stable fixed point, we introduce diffusion, nothing happens. In fact, this isn't the case. The introduction of the diffusion here can actually destabilise this fixed point in a spatial sense, and you can get spontaneous patterns or spatial structures emerging in a model like this. If you have a stable fixed point without the presence of diffusion. And Turing suggested that this might be a possible mechanism for pattern formation in nature. So as we've seen, it can't explain everything. So the best model for some things, such as the somite segmentation process, would be like a clock-wavefront model or something like this. So clearly there's kind of a sort of theory of the gaps, so it's not going to explain everything in nature. And there are problems with it, which I'll go into, but I'd like to try and convince you first that perhaps it has some validity, or we should look at this as a possible mechanism in some circumstances. So, kind of a nice example where Turing's...
Is that a real fish on the previous slide?
Yeah,
computer?
That's emperor angelfish. And I'm subtly suggesting here this is a chemical pattern which looks a little bit like it. So my sense of hypnosis. Yes. So well, here's another angelfish actually, with slightly different patterns, but it has these really kind of characteristic stripes, if you like, and they've got these sort of zippers. So you have these kind of intersections here, and these can be rather nicely replicated by reaction-diffusion models. So these kinds of defects and so forth, you can recreate these rather nicely. So qualitatively, certainly this reaction-diffusion model is doing a good job at replicating some of the patterns that we see in nature. Okay, well we can go further. So at some level, this reaction-diffusion mechanism has to connect with the underlying genetics. So the idea would be that certain genes would produce certain chemicals which would interact and cause the production of this pattern. So what one can do is, if you know the gene which you think is responsible for the pattern formation in a particular organism, you can cause mutations to this gene on various alleles. And this is what Kondo did, this is a Japanese group. You cause these various mutations, and what you find is that you get this whole array of different patterns ranging from stripes to very sparsely distributed spots. And what we can do is you can replicate the stripes and spots that you see in the lab with just by varying one parameter of the reaction-diffusion equations. So you can recreate these patterns quite nicely. So somehow there's this. It seems like there might be this link between the underlying genetics and some sort of reaction-diffusion mechanism, possibly. My favourite example of where this theory seems to be doing something quite nice is, you can take a zebrafish in the lab and you can ablate some of the pigment cells that make up the stripes, leaving a gap. Now, if the stripes were solely determined by the underlying genetics, that is, the genes are telling the stripes exactly where to go, then what you would expect is that as the animal heals, the stripes will just reappear. This, in fact, is not what happens. Instead, you get this kind of strange bleeding of the stripe below into the gap. And this is recreated again rather nicely by the reaction-diffusion model. So again, you get this kind of bleeding of the stripe below into the gap. And so you're getting something. You're sort of getting something for nothing, obviously. Your theory is predicting something unexpected which you didn't put into it. So this is sort of evidence that maybe there's some sort of reaction-diffusion type of mechanism going on here. However, so people have not yet been able to identify pairs of morphogens which react and diffuse in the way that Turing predicted, and they can't show this direct link between the genes and the pattern formation. But people have managed to identify sets of chemicals in the lab which do produce patterns like this. So they've managed to find chemicals which give rise to Turing's mechanism. However, it wasn't until the early 1990s that people actually managed to find sets of chemicals which would do this. So what was the problem? What was it that made it so that people couldn't find these sets of chemicals? Because if the chemists can't find the chemicals, then maybe nature can't in an evolutionary manner as well, and that's a problem. So the issue was that in order for Turing's mechanism to work, most often, what you have to have is rather different diffusion coefficients for one chemical species and the other. And that's kind of unphysical, because if you were to put two chemicals in the same sort of environment, you would expect them to have roughly similar diffusion coefficients if the size of the molecules were similar. So either you have to have these very different diffusion coefficients in order to get this pattern formation, or you have to fine-tune the reaction rates, and that's kind of cheating, isn't it? And so this is why we call this the fine-tuning issue. And two possible solutions have been suggested for this in the literature. So one is the inclusion of intrinsic noise, because what happens here is, in kind of a similar way that we've got these noise-induced cycles in the gene expression model, so you could have ranges of parameters that you saw, so there's a greater range of parameter sets for which you will see cycles in the gene expression model than you would do in the deterministic system. In this system, you'll see a greater range of diffusion coefficients which will see patterns than you would do in Turing's original model. So in this sense, intrinsic noise can sort of mitigate this issue and make it so that the diffusion coefficients don't have to be quite so far apart. And I'll kind of show you what I mean by that in a bit more detail in the next slide. But furthermore, so another possible solution to this is the inclusion of so-called anomalous diffusion effects, which make it, again, so that the ratio of the diffusion coefficients required for pattern formation is not quite so great as it would be in a normally diffusive case. Okay, and so what we do to test, right, so what we thought was, okay, so you have these two solutions, how about we put them together? Okay, so we've got this non-Markovian anomalous diffusion, and we've got the intrinsic noise that comes about due to having an individual-based model. So what we do is we start with our individual-based model again. We write down a path integral for this model, and we do our system size expansion, and eventually what we arrive at is a set of equations that look quite a lot like Turing's, but with some key differences. So we have a rather ugly looking fractional diffusion term here, where we have this fractional derivative, which is manifestly non-Markovian. So this is dependent upon the history of the system. So this is where our non-Markovian effects are coming in due to the subdiffusion. And also we have these integrals over time in the exponents here. So this is our anomalous diffusion term, which is clearly very different to the diffusion term in Turing. We also have the reaction terms, which are very similar. But now, crucially, we have the inclusion of this coloured noise term. So this is reflecting the individual-based nature of the interactions, processes, kind of approximation for large numbers of particles again. And this is so rather nicely, so this is a coloured noise term. So the noise now is dependent upon the noise in the past, and this is also reflecting the kind of non-Markovian nature of the dynamics.
Sorry, I got lost. Which is your individual case model that gives rise to this? So you'll have particles which will, so we've got two types of particles. Locally, they interact with one another in a stochastic manner, so you'll have certain reaction rates which will be dependent upon the number of particles that you have at a particular site. They also hop from site to site, and you can take a case model if you like. But the way that they hop is dependent upon the amount of time for which they've been there. And so having this time-dependent hopping kernel, you get this fractional derivative out, and you have this subdiffusion. So if I were to ignore all the reactions, we would just have a fractional diffusion equation, essentially. The basic idea is that the time to jump depends on the time you have been on a particular site.
Exactly. Yes. And in that sense, it's not Markovian.
And it decreases. I mean, the probability of jumping decreases with the time you have been in a particular time? Or
yes, that's what gives rise to
called aging, right?
Yes. Yes, it's the mid-time level function.
So you are not implying that anomalous diffusion is always associated with non-Markovian? Or are you?
Sure. Because, yeah, sure. Because the rate at which you're hopping from site to site depends on how long you've been there.
So is this the only way that you can get anomalous application?
No. So you can have kind of fractal diffusion as well. Oh, I see what you mean. Okay, so there are various ways that you can generate some diffusion, yes. This is the one that I chose.
What is P?
So P is the death rate. So I chose not to define it here. But so if I split up the reaction rates into birth and death, this would simply be the death rate, which is dependent upon the concentrations of the molecules. Okay. Right, if there are any questions, I'll proceed. So what we can, so now that we've written down this equation, we can do an analysis, and we can also run simulations of the full individual-based system and compare the two. So what we find... Sure.
So DJ is a coefficient? It's a thick height?
Yeah.
That's not very big.
No, that's a diffusion coefficient, yes. Okay. So this will obviously be related to the hopping kernel that I choose. So all of this comes, we derive this as a result of that individual case model. So this is an approximation to the dynamics. Okay. So what we find is that, so for sets of parameters which for which one would expect normal Turing patterns, we still see the Turing patterns, albeit modulated by noise, to get these kind of noisy Turing patterns. Well, let's suppose that we reduce the ratio of the diffusion coefficient such that we wouldn't expect to have Turing patterns if we were just looking at the deterministic model. Then what we find is that we still have a kind of a pattern being produced, which is slightly more noisy, admittedly, but we wouldn't expect this to be there at all. We just expect a flat line if we didn't include the intrinsic noise effects. And just to convince you that this is really a pattern and not just noise, I've compared for a parameter set for which we don't expect any pattern at all, and this is just this is the noise just to compare. And one can produce a criterion for stochastic pattern formation of this type. So patterns where you wouldn't expect it from the deterministic system by looking at the power spectrum fluctuations again, except this time with respect, so we're taking the Fourier transform with respect to a spatial variable. And if we have a peak in the power spectrum like this, then we say that we have these kinds of noise-induced patterns. And so this is our theory line here that we produced, and these are individual-based simulations. You see that very quite nice. And then what one can do is, so if we can produce this line with our theory, we can analyse for what sets of parameters we get these noise-induced patterns, and so we can produce a kind of phase diagram where on the x-axis here I have the degree to which the dynamics is subdiffusive, and on the y-axis here I have the ratio of the diffusion coefficients required in order for the patterns to form. Now remember, the fine-tuning issue that we're looking at is the fact that you need very different diffusion coefficients in order for patterns to form in Turing's original model. So this would be kind of Turing's original model here, so just the normal reaction-diffusion equations with no noise and no subdiffusion. As we increase the noise, we see that this is reduced. So this is kind of mitigating this, as we increase the subdiffusion, the ratio of the diffusion coefficients is reduced. So this is kind of mitigating the problem. As we introduce intrinsic noise into the system, we take into account intrinsic noise, we get these stochastic patterns forming. And this reduces the threshold of pattern formation even further. So in a sense, the combination of these two solutions works better than this diagram. So I'll point out as well, so the oscillation, so this pattern here corresponds to these points of the phase diagram here. Okay. So that's more or less everything I want to say on this Turing patterns issue. So to conclude, I hope I've convinced you that in certain circumstances it's important to include intrinsic noise in these models, these individual-based models, because for certain parameter sets, the individual-based model will give rise to emergent phenomena such as cycles and patterns which are deterministic mean field approach groups. Furthermore, if you want to calculate this intrinsic noise, and you want to see if interest related to this noise, one can use a kind of path integral approach when the system is non-Markovian and you can't write down the equation. And I showed you two examples of where this might be useful. So this was the somite segmentation clock, where we have these noisy cycles, these noise-induced cycles, and I showed that in our model. As we increased the strength of delta-notch signaling, not only did the synchronisation between cycles increase, the quality of the cycles also was affected and improved by the strength of delta-notch signaling. And then we looked at Turing pattern formation, where we had these noise-induced patterns which increased the range of parameters for which we saw pattern formation, and I showed that we discussed the idea that perhaps a combination of anomalous diffusion and stochasticity could mitigate this fine-tuning problem that we see with Turing pattern formation. Okay, so we have these two papers if you'd like to read a little bit more about this, and I'd like to thank the EPSRC for funding me for 3 years, and thank you for listening.
How do you define the threshold with the pattern formation windows?
So
the line you know, how do you define that?
So say that. So our criterion is that if this peak pops above this value for Q at 0, then we say that we have stochastic patterns.
So if the pattern is, the component is larger than the generator,
Exactly.
then you define that as threshold.
That's our threshold. So, I mean, one caveat to that is that if you go, so there's a reason that I picked a dot quite close to the line there. So admittedly, if we go quite far away from the line, so where the peak is only just appearing above the threshold, then patterns aren't quite so recognisable. That's certainly true. But that's how I draw the line anyway. So that's where I say it's on test. The point is that it expands the parameter range to a certain extent.
Thinking about the previous example with the somitogenesis block, so what you present, you have your deterministic system, so without noise, has no oscillations. Then when you consider, I mean, these intrinsic noise effects and you have oscillations, this somehow remembers, I don't know if it's related on some topic that was quite popular many years, some decades ago, of noisy precursions of bifurcation points. So think about you are close to bifurcation but below, then your system is not oscillated, then with noise in an appropriate way, I mean, then you, I mean, anticipate the appearance of bifurcation, and then you have oscillations in some manner. So my question is, in this problem, so this was an introduction, my question is, in this problem you chose some set of parameters, okay, some physiologically reasonable set of parameters, you have no oscillations, and I have oscillations. Do you have some, or can you envision some way of systematically, I mean, studying how close are these set of parameters? So you, I mean, for this particular set of parameters, you obtain this behavior, no oscillations in the deterministic limit, oscillations in the noises. How is this typical? I mean, so if you use other set of parameters, you obtain. So how far are you from the whole bifurcation? In my view, I mean, it's different from your perspective. If you use other set of parameters, you don't obtain this enhancement in the set of oscillations. If you use other set of parameters, I mean, the behavior is the same because both the deterministic and the noises. So, do you think it's possible to quantify in some way?
You could certainly
confusion as particular set of parameters makes me this thing. How is this general?
It's, well, so from what I've seen simulating this and looking at various parameter sets, it certainly seems a very general feature, and in all sorts of different models, as you rightly say, you get this kind of preemptive cycles in the noisy model before you arrive at the bifurcation point or the phase transition to where you have emergence of a limit cycle or something like this. This seems to be very general, because essentially what you have to have is so when you cross this bifurcation point, essentially the real part of your eigenvalue is crossing from being negative to being positive, isn't it? And just below this bifurcation point, you'll have quite a small in magnitude real part, so that the oscillations decay at a very slow rate. And essentially what the noise does is kind of keep these oscillations going around. So that's going to be a general feature, and you can reproduce this with extrinsic. So speaking to, well, so you'll definitely get these noise-induced oscillations all the time. Well, not all the time, but in a lot of different scenarios. But I think, so you're asking as well about certain parameter ranges for which you'll get maybe fixed points and maybe whether these are biologically relevant. So I'm not sure I want to make a statement on that, because this is a very reduced model, and as such, it's not particularly useful to say, okay, for this set of parameters I get this and so forth. I think what I really want to say is that, okay, reasonable that you might get these noise-induced oscillations for a particular parameter set, which might be biologically relevant. So when you're doing more detailed models in a biological setting, you should watch out for this if you're looking for cycles. Because I've seen studies where people do like these parameter searches in a very complex model, and they'll do it for just deterministic equations, and that's not, you're missing out on the noisy cycles. So that's kind of what I wanted to say. Does that answer your question?
Yes, somehow.
Okay, we can talk about it.
And theoretically, you think that you are really, the parameters in which the experiments that the experimental labs are doing, are really, below the deterministic point of oscillations, and then noise is enhancing, or not? Do you have some clue?
It's hard to say, because the cycles that you would observe even in the deterministic, they look kind of qualitatively similar. So I couldn't tell you from, obviously you read the papers and you can see these cycles in the Gini expression. It's like, can I tell from just looking at that if that's a noise-induced cycle or not? No, I couldn't tell. I don't think you could tell unless you built, like say, a really intricate model of the system, and and then just looked at the parameters and then literally run the deterministic system. Is there cycles there? No, but we see cycles and then it's noise induced. That's all I can say.
Maybe a follow-up question, short one. Is this an example of what people used to call coherence resonance? Have you heard of this?
Coherence resonance?
Yes, well, it is this noise-induced oscillations, and the effect in some of these systems is that if you look at the coherence of these oscillations as a function of the noise strength, we'll find that the most coherent pattern you observe is one for an intermediate noise strength, neither too low nor too high. And you haven't varied your noise in your example, and you start from this discrete model, which is not what is usually looked at. Sure. But still, I wonder whether this is not.
You also have system size of it. Noise induced is very bad in system size. It was all my question.
Yeah, well, yeah, my question would be whether this can be related with the existing knowledge of coherent resonance.
What kind of field of study is this? Just very general complex systems?
Yes, it is general complex systems.
Okay, so I've not heard of the specific term before. However, I would say that what we saw in the somite segmentation clock example certainly was a kind of resonance, right? Because you did get this kind of amplification of the cycles and this increasing coherence, as you say, and I've certainly characterized it that way. I've not heard the label coherence resonance before, so I can't put in more detail on that.
So my answer would be no. We can.
Yeah, we should talk.
Can you easy to describe briefly how do you modify the QSP algorithm to take into account delay?
Yeah, so it's actually easier than you would think. Although, so you have to be careful to make sure that the statistics are obviously conserved by your algorithm. But simply what one does is, okay, so a delayed reaction is triggered. You make a list of all the delayed reactions which have to be taken into account at a later time. And then when that later time comes, you just do the reaction basically. So the triggers happen in a stochastic manner, and then you keep a list.
Instead of producing the effect now, you wait for
exactly. Of course, you may also have effects which have zero delay, and that would be kind of, you just perform these in a standard Gillespie way, but you have to keep this list. It's called next reaction method. Yeah, so I was surprised how simple it was, but it works.
Any other?
So you told me that the only thing that you obtain from theory, I suppose, is the power spectrum. No?
Need examples? I think yes. Yeah.
Okay, so you obtain, for example, this comes from the power spectrum. So the trajectories are from the Gillespie algorithm.
The points, so like this, these points here. Yes, these are from this modified Gillespie algorithm.
And the one in the left also.
Yes, so these are individual-based simulations. Yes. So I'm not simulating the SDE, although they do have their uses actually. So we work with some biologists in Manchester where they use these stochastic differential equations in. So if they want to know if it might really complicated models via cycles or not, they can simulate these stochastic differential equations. Because sometimes, so not to get too technical, but in order to produce this curve, we make a linear noise approximation about a fixed point. So suppose that it really matters. So the noise terms that you get are often multiplicative. Suppose you can't make this approximation that you're at a fixed point, then you have to simulate the full SDE so it can be useful in those circumstances. Okay.
Right, if there are no more questions, let's Joe again. He's here until Friday afternoon.
See you.